Hello, everyone, and welcome to the second event of DESECON Netherlands. Today, with me, I have Stefan Petrushesi from GitHub. He's going to talk about bug bounties and pen test, how to get the best out of it. Before I bring Stefan to stage, I just want to say that DevSecOn is a global community, an inclusive community that educates and enables the developers in application security. And I'm Davide Cioccia, the chapter lead of DevSecOn Netherlands, founder of the Codex. So let me bring Stefan on stage. There we go. Hello, Stefan.
Hello, guys. Hi, Davide.
How are you?
I'm all right. Yourself?
Pretty good, pretty good. Ready to hear your talk, and I know you have a demo for us today. So
I thought you were gonna
pretty
say
excited to see that.
For the weekend, man.
For a long weekend, actually, in the Netherlands, Monday is holiday. So
Oh yeah.
Are you ready?
I'm ready for the long weekend as well.
Yeah, hopefully the weather will be good. But
it will.
Who knows?
It always is. It always is.
All right. Yes. All right. So I know you have a presentation. I'll put it on stage. There we go. And well, Stefan, the stage is yours.
Thank you, Davide. First, yeah, thanks for inviting me and giving me the opportunity to join you on this meetup. Looking forward to, well, basically the feedback. I'll try to share some experiences and knowledge that that I thought it's useful to be shared with the community, and looking forward to the feedback. I do hope it's going to be a bit of an interactive one as well. There is some demos at the end, so stay tuned, stay till the end, because you know how demos are, it's expected to fail. So, and that's always fun to see. So stick around. So I'll start with the presentation. The format is we're gonna look at some presentation slides and explain what's going on and what my point is, and then we're gonna look at the demos at the end. So the topic of today is how do we actually make the most of our bug bounty programs and pen testing programs, right? So first, just a real brief introduction. As Davide mentioned, my name is Stefan Petrushevsky, security solution architect, part of GitHub and the GitHub Professional Services. Have been in cybersecurity for a while now, 10 plus years, been around for a bit, done a fair share and worked in multiple verticals. The last 4 or 5 years mostly have been doing work and focusing on DevSecOps and AppSec overall. The agenda for today is first we're going to look at what AppSec program today usually means. Then we'll look at the bug bounty scene currently, see if it's actually there, if it's something we should care about, we should get involved or not, or is it a thing? Then we'll look at and think about what we can actually do better for our application security program and bug bounties and pen testing. Then we'll look, of course, how GitHub could potentially help to do things better when it comes to implementation of your AppSec program, and we'll close off with 2 examples and 2 demos, one with CodeQL and one involved secret scanning. All right, so where are we at currently in the world? What does application AppSec program currently means, and what is the drive that most of the companies now have? I think we will all agree that the shift left buzzword, it is a buzzword in a true sense of the word, but it also is something that we have to do. Why does everyone agrees or understands that shifting left is a good thing to do? Well, simply if we look at pretty much any report and statistic for the past years on the cost of data breach, and therefore the cost of fixing a bug in each of the stages of a development lifecycle. We all know that they will all show, and we all know that the breach that happens after deployment costs a lot more than what the remediation of that breach costs a lot more than us remediating a vulnerability earlier in the process. The earlier, the better, because the remediation cost just goes down. And as can be seen from this stat report, the remediation cost for fixing a vulnerability in the development phase of the process is $80 versus the $3.9 million if that is which is the cost for remediating a vulnerability after a breach happens in production. So we all are working, and we all are going and shifting to the left. That's, I think we will all agree. Now, what does shift left means in practice? There are multiple interpretations and there are multiple implementation of an SSDLC and application security program in company by company cases, but overall it can be represented, or this is one representation of it. So you have pretty much, the idea is to have security in all phases in the development in the software development lifecycle. So even from the start of project inception and project configuration, by defining the platform security and the policies, then during the code, we of course have peer reviews and pull requests that are being reviewed, an actual code review on commit, and code review of course can be done manually and or by automated toolings. The usual suspects here, of course, automation by using a SAS tool and an SCA tool. Further on, when it comes to, we introduce a security aspect also in the CI/CD testing by introducing a dust tooling, and of course that goes on all the way to with the other controls, which I'm just gonna skip for now because it's not the topic of discussion. But the idea is that we have a security control and hopefully automated security test in each of the phases of the development process. Each code or each project hopefully gets released and gets shipped, and then what do we do after? And what we see currently in an AppSec programs in companies is that they all introduce, or not all, but companies tend to start and introduce a responsible disclosure, a bug bounty programs, and of course they do pen testing after shipping. Now, is bug bounty a thing? Because a lot of companies have started doing it. The amount of people doing bug bounties has been increasing constantly in the past years. So is it a thing? It definitely is. We can check that and we can confirm that by just looking at the numbers from the reports from last year. So I looked at the HackerOne report, and I looked at some of the bug bounty programs reports from Google and Microsoft, and it's pretty evident. So last year on HackerOne, the number of verified vulnerabilities increased by 20% compared to the previous year, 2021, with a total count of 66K of verified vulnerabilities. The increase is also evident when it comes to the median bounty that is being paid out, that has been paid out on HackerOne, and the median price from last year is $3,000, which is a 20% increase from the previous year. So the vulnerabilities are, it's evident, and the conclusion is that the vulnerabilities are becoming expensive even when it comes to paying that out through a bug bounty program. The previous one, 20% of 3,000 should be 2,500 was the median price of the previous year. Google has paid out in total for last year 8.7 million in bug bounties, which is 30% more than the previous year. And Microsoft has paid out approximately the same as the previous year, so 13.6 million, with a noticeable increase in eligible reports that are submitted, meaning there are a lot more bug bounty hunters, there are a lot more bug bounty submissions, there are a lot more vulnerabilities that are being found by a bug bounty by the bug bounty hunters through the bug bounty programs. So now that we know that bug bounties are a thing, and we know that most of the companies that also do pen testing programs, most of them do pen testing, excuse me. So what we can do better? So apparently we have more vulnerabilities coming in. We have more vulnerabilities being found after we ship to production. So what are we doing wrong? Are we doing everything wrong, or is our OPSEC program completely wrong? Well, that it has been shown, and researchers has shown, that shifting left and doing security frequently in each of the stages eventually is better in results. So that's definitely when it comes to finding and not introducing vulnerabilities. So that's definitely not the case that the whole application security program is just wrong. The bug bounty programs and the pen tests are there. They are producing results. That's also good, because it's better that we get that vulnerability from a bug bounty hunter than from an actual malicious actor that exploits it in production and, of course, uses it to breach into our organization. So what can we actually do better? I was actually curious on if the audience has any ideas on what they're trying to do different than a traditional OPSEC program in their companies or organizations. So I don't know, David, I'm not sure if the audience can chat and can speak.
Yeah, they can not speak, but definitely chat, write comments under the YouTube channel. So let's see.
Yeah, so if you have ideas other than what I'll present now, then I'm happy to discuss that towards the end, and have an open discussion, at least in the chat, and hopefully next time, if we're live, we can do it also live.
And this will be recorded also, so we can collect comments in the Discord channel. So if you go to DevSecOn website, you have the Discord channel, this DevSecOn Netherlands, and then we can collect also questions, answers, feedback, everything.
Cool, thanks. Then since you can talk, what is your personal opinion, or professional opinion, of course, when it comes to like bug bounty programs and pen testing programs and the current state of application security programs in the world? Are we doing? Can we do something different? Can we do something better? What's your idea? What are you trying to do in your respective companies or for your respective clients?
Well, when it comes to bug bounty, I mean, I've seen it implemented from different companies in different ways. And what differs, I mean, how the implementation is the same, of course, but what differs is how you handle the bug bounty problem. How do you react? What do you do with those findings? And that's really different from companies to companies based on the maturity level of that company. And when I say maturity level, I mean security maturity. So does the company have a security team that can handle those findings, that can verify those findings? Who is gonna read the reports? Who is gonna do the triage of the findings? And one important thing that I think I've seen like a few times, and I try also to communicate to our customers, to learn from bug bounty programs. And I think we have something in this presentation as well. Like you get the findings, you verify the findings, their valid findings. Okay, what happens? You create a patch and that's it, and you forget about that, or you learn from that. You try to automate that control, that test. You create tests for it, so you can replicate that to your products, multiple products, right? So it really depends on the level of the company, the maturity level of the company, I believe. But it's definitely something that that works, right? It helps to identify, bugs that maybe you missed during development, and of course, or complex findings, or just low-hanging fruits. But
no, you're spot on when you say you need to have first and foremost someone and people that will actually go over those bug bounty reports, triage them, hunt down or track down, find the root cause and fix that. Like that's the first basic step that you need to have, and that's not always easy for companies in the first place. However, yes, there are a lot of, and we've seen also in the reports from HackerOne that just the bug bounty programs are on the rise. So companies are getting there. They are getting reports, they are addressing findings, and vulnerabilities are getting patched before a malicious actor exploits them. So that's cool, right? But what you mentioned also just now is like, can we do more by learning from that, and how do we structure, or how do we use that lessons learned step of the process to improve our SSDLC, right? Or our implementation of the SSDLC and our application security program. And that's what what I was planning and hoping to share with you. It's not a groundbreaking idea. It's I would assume for most people, it would maybe either be something that they already do, or it just sounds and it is a common sense. So what does that mean, right? So we get findings from our vulnerability response, responsible disclosure, bug bounties, and pen tests, right? Then there is a team that goes about, analyzes them, and learns from it, tracks down the root cause, tracks down what the vulnerability is, and fixes it, right? Now, from here, we need to think on how we can actually do more. And we discussed and we mentioned earlier that a lot of the security testing is automated. And can we actually think of ways how to use the bug bounty reports and the pen test reports, or the findings from the pen test reports, to codify them and test for those through continuously for other projects that we have in or for through our whole code base, and do that continuously for current releases and new releases and future releases, right? So that's the idea of this presentation today, or this talk, is how do we learn from it, and how can we actually codify some of that to find more? Is it at all possible? Definitely is. I'm not reinventing or inventing anything here. So it is being done. It is an approach that some companies have adopted already. I just wanted to share and showcase it here, right? So the idea is learn, analyze, codify, automate, test, and find more of the vulnerabilities today and in future, and that make that be part of the SSDLC. Now, in order for me to explain that in practice and how we see it at GitHub, I'll have to introduce a tiny bit on GitHub Advanced Security and what it is, because it will be shown also in the demos, and some companies are using it for this particular case that I explained, or approach that I explained. So if we look at the current capabilities of GitHub Advanced Security, then we can sort of have three areas where the capabilities fall into, and that's supply, code, and development lifecycle. So the supply chain is pretty much looking for in your dependency graph, finding the dependencies of your project, and using a advisory database of known vulnerabilities that have been published. Check for those in your code base and your projects, and get notifications and alerts and hopefully update them and fix them by submitting a automated PR. Then in the code area, we have the secret scanning, which is finding secrets in your code base that are exposed. And I'm sure all of us has read or seen one case or one bug bounty submission involving this. And the code scanning is analyze the code and find vulnerabilities by utilizing and using the CodeQL. I'll get to CodeQL a bit later. The development lifecycle, it's not really relevant. So for this protection, for this presentation, excuse me, but it does involve like security overview, have an overview of the whole enterprise organization or repo level, have branch protection and signing of commits and so on. We're not gonna get into those too much. So supply chain translates pretty much into Dependabot, which is is one of the tools that we have in Advanced Security. What it does is automatically raises alerts when the vulnerable dependencies in your code are detected. It creates those PRs to fix the vulnerabilities. It does send notifications, of course, and it just shortens the time for a known vulnerability to be fixed when we look at the numbers in practice. Then we have code scanning. Code scanning is basically the tool that we use to find vulnerabilities before they are merged into the code base with CodeQL. Of course, CodeQL is not the only tool you can use, but for this presentation, we will focus on CodeQL because you can scan your code and feed results into code scanning to GitHub from any of your, any SaaS tool pretty much that supports a particular output, results in a particular format called Satif, or you can just simply upload them. So this approach will show the demo in CodeQL, but I assume it can be done in your other SaaS tools that you use, products that you use. So it integrates directly. It integrates the results directly into the developer workflow. As you can see from the screenshots, we are in GitHub. Doesn't necessarily need to be .com, but we are at the UI, and you see the vulnerabilities. So we see the code, the vulnerable code. You get all the necessary information to fix it, and so on. You can write and define custom queries for it, and it's very much, as I said, extensible with and support for other SaaS tools. Then the secret scanning is again a rather simple one as a concept. It just searches and finds secrets across your code base during the entire Git history. So that's an interesting one because a bug bounty program might submit a secret that you would want to. By fixing it, you need to actually look throughout the whole history potentially and remove it. So secret scanning can help with that. It has a push protection which helps you prevent the submission and addition of secrets to your code repos. You do get alerts, of course. You can easily exclude false positives because false positives are there. False positives will be there when it's all about tuning and making that number small from any automated security automated testing tooling. So now we get to the demo and how we could actually, it's basically two demos. One is showcasing a vulnerability that has been published, which then was translated into a CodeQL query, which was used to find vulnerabilities in other open source projects. We're going to look at one case, and then we're going to look at how that actually looks like in practice and how does that querying works. Just for you to get familiar a bit and see a bit of CodeQL in action. Before we get there, we need to. I wanted to briefly explain how CodeQL works. It's not an easy thing to do and explain it in great detail, and that's not the purpose of this presentation. Maybe in future we can look at it, but in CodeQL, the code that you have for your project is treated like data. You can execute queries against databases which are extracted from the code, right? So as you can see in this, so you have a code base and you have build system and you have artifacts. There is something called extractor, so which CodeQL uses. So basically CodeQL, to create a database, first extracts a single relational representation of each of the source files in your code base and stores that in a separate database. So for compiled languages, there are differences when it comes to compiled languages and interpreted languages, right? So for the compiled languages, it requires the build process. And basically what it does is extracts, the extraction works by monitoring the build process. And each time a compiler is invoked to process a source file, a copy of that file is made, and the relevant information is stored. Well, the relevant information about the source code is collected and stored. So what does the relevant information means? So this includes the syntactic data about the abstract syntax tree, required one, and the semantic data about the bindings and so on. For the interpreted languages, the extractor runs directly on the source code, so it does not require the build process, resolves all the dependencies, and gives an accurate representation of that and stores it into a database. So you have extractor, which then translates into trap files. It uses the trap importer, and a CodeQL database is created. Now, once we have that CodeQL database, we can simply go about and execute queries. The queries, CodeQL queries, well, are supported by CodeQL query libraries. You can write queries, custom ones, or execute queries that have been already published. Now as you'll note here, and I guess it's pretty obvious that you have something that is called CodeQL database. So potentially, what we could do here is think about maybe including this into your private bug bounty programs, right? So people can actually use CodeQL to do research and potentially find more vulnerabilities and submit that as bug bounty submissions. Mozilla, since 2019, has introduced that and pretty much invites security researchers to write queries to find vulnerabilities in current or past versions in Mozilla, and submit those as bug bounty requests, submissions, sorry. So that's one case of a company. We've seen recently Trail of Bits publishing some information about using CodeQL for security research and finding vulnerabilities and exploiting them, or finding vulnerabilities and expanding the search for them. There are also some nice, and I think Jordi Zomer, some of you might know him because he's, I believe, from the Netherlands. He has also been using that to codify the Sequoia bug discovery, and so on. So just an examples. Microsoft as well is using using CodeQL for a very long time, and the case that we'll look at actually involves Microsoft, which is interesting to see, in my opinion. So this is what, so we have CodeQL now as a concept. We can write queries to find vulnerabilities in our code base, in essence, right? So how do we use that in our pen testing, bug bounty, responsible disclosure programs? So you have a submission, which eventually results in a security bug. Then your security team or your responsible team goes about, diagnoses the problem, finds the root cause, and fixes the original issue, right? And usually in usually in companies, this process might stop here. Now, how about doing something more with this information? And what I explained earlier, that doing something more means let's figure out if we can codify this and find variants of the security bug that we have received through our bug bounty program, analyzed, fixes the original bug. But let's try to think how we can codify that in CodeQL so we can actually find variants of the bug in all of our code base, right? How does that work? So you write an, usually you get the information, you write an initial query, you run that, you find some bugs, you might find a lot of false positives, you refine the query, you improve the query, you run it again, and hopefully find more variants of the original bug that was submitted against one of your assets through a bug bounty program in another asset, right? And then, of course, you can use Advanced Security to continuously monitor and prevent, of course, to introduce future bugs. So not what we only scan for a variant of a bug bounty submission in the current code, but we also do that in future, because once we codify that and we write a CodeQL query, we can run it, well, anywhere against anything, right? That makes sense, of course. So let's look at one example that we've seen, and it's an interesting one just to showcase how this works in practice, and have we actually seen it in practice, and have we done it in practice. So we'll look at the zip slip vulnerability. The original research can be found in a post from SNCC, and what it actually is, it's how programming languages and applications extract and unzip zip files. So a zip file, you would see it as a representation, and you can find something like paths and associated content. When you extract those, it takes the path, it takes the content, stores the content to the path that is defined. Now, the usual, like the WinZip and the 7-zips and stuff, and such archive programs do not necessarily allow you to create arbitrary paths and file names. However, that is possible, and you can craft a zip file which might contain something like this. So it has two files, and you have a good one, a good SH, and you have an evil SH. Now, the evil SH, actually, the path, as you can see, it includes a traversal back. So what commonly happens is a application would take that file. So it will take all the entries, meaning the good one and dot slash all the way to temp evil.sh. So it will take the two, and for each entry, it will just take a file or create a file with the name good sh or traversal to evil shell, and then just treat the content as input stream, and eventually copy the contents to the destination folder, the destination directory and file. In this case, if we look at the malicious one with directory traversal, it means it will go all the way to the temporary folder, the TMP folder, and it will create an evil sh file.
Stefan, if you can zoom in a little bit, I think it's better for the, yes, that's okay. Better. Okay, perfect.
Yeah, so I mean, I'll share the link, or you can share the link, David.
Yeah, it's already in the chat. And,
okay, cool.
Yeah.
So that's the so what happened? So that's the vulnerability. Now that we know what the vulnerability is and it has been disclosed, what happens is, how do we actually write queries? And what happened in practice is that GitHub customers created CodeQL queries to identify and search for this zip slip vulnerability in their code bases, right? Now, the cool thing about CodeQL and the queries is that those queries are public and open source by the community. And actually, Microsoft went about, and because it's commonly used, or it is used and can be, projects using C# do handle zip files. You can imagine that's a use case that an application might do that is written in C#. So what Microsoft did is wrote a query, was persuaded to publish it or just wanted to publish it and open source it, and included it to the default public CodeQL pack. So this is the submission itself. It happened on the 16th of August, just a few days. I think it's like 8 days or something after the zip slip has been and vulnerability or research has been published. So now that this is submitted as a standard query, it can be run from CodeQL by any customer and any user against any code base, right? The query itself, I mean, we don't necessarily, this is of course an optimized one, and it looks at a lot of cases. What we'll see later is just a simplified query of this or version of this. But the point is, there was a submission, a query was written, and then, you know, this public query started being used by everyone to scan for vulnerabilities elsewhere. So now that it's open sourced, a lot more was found, and one of them, funnily enough, and GitHub also scans open source projects and runs CodeQL queries against them. So what happened is that Microsoft coded a query, published it and open sourced it, and then it was used to actually scan their other projects, in this case PowerShell, for the same vulnerability, and it turned out that that vulnerability existed in PowerShell. So that vulnerability was found, and of course PowerShell is pretty big, so this, you can imagine the impact that just from one research, writing one query, to finding vulnerabilities or finding that vulnerability in open source projects. So the impact and the community impact is just great, and I just love to see. That's what you love to see. Now, well, actually, we can now look at just the vulnerability and how that CodeQL query looks. Now, this might be a bit trickier to see, so I'll try to zoom in.
Yeah, let's make it big. That's good enough, I guess.
So what I have here is the PowerShell source code with the reintroduced vulnerability. What I've done before, I've built and created that CodeQL database, and I've loaded it in my VS Code. So we're using VS Code usually to write and run queries. There is an extension you download simply. Then I just imported, well, I created the database and just imported it to my VS Code CodeQL extension. It's already set as the current database that we will run queries on. So how does what is the vulnerability here? Basically, the magic happens in this for each loop, where we take entries from a zip archive, and for each of this entry in the archive, we would construct a path with the entry of an instance of a class zip archive entry, use the full name, remember // and combine it and concatenate it, well, to create a path to the destination folder that includes the full name, right? And then what we'll do is we will call extract file, and this is, by the way, the source code from PowerShell that we're looking at. And what we'll do is call an extract to file with the path that we've created. Essentially, with the // this leading to copying the contents to the path, which is // all the way to temp evil sh. So that's where the vulnerability lives. Now, how do we actually write a query? We can write our own query, or we can reuse a query. So this one in itself is the zip slip query that has been written and published and is now part of the default code pack, query pack. sorry, we can simply run this against our code base, and our code base now being PowerShell. We can run the query. It can take a bit, and we will see this query would find the same vulnerability or the same code that I've just explained and walked through. Now, it might be better for showcasing to also explain the approach as initially discussed, and that is you get a bug bounty report, you find a vulnerability, you write a first query, you find the initial variance, it might not be the refined, then you improve the query to exclude false positives or find more variants, and so on. So the simplest of versions is this query, right? So we'll use a property in C#. We'll define a property, a C# property, and a method call. As you remember, we have a method call pretty much, and we have a property, which is entry, right? And we have a property, sorry, which is full name. So we're looking for zip archive entries or property in a zip in an instance of a zip archive entry called full name, and we're looking for a call, a method call to extract to file. Now, by using taint tracking, we're effectively looking for the taint tracking from the source to sink, and we're basically looking for access to the property full name, entry.fullname, access to the property that flows all the way to a call, extract to file, where that property is used as a argument 1. And then we do a select, so the format is from where select of a query. So property call, what I explained about a property with full name, that access to a property of full name that flows to a call to extract file as argument 1 and print that out or find all instances. Now, if we run this query, we should get the same report or the same vulnerable code sample. Yeah, that's okay. So as you'll see here, we got again one result, and it is the same result. So luckily there are no zip slip vulnerabilities elsewhere except for the one that I reintroduced in PowerShell. But if there were, this query would have found them in other files as well.
Cool. Question.
Yes.
If you implement a control like to prevent the // before that, will that query understand that, or you need to modify?
Yeah, that's a very good question, Davide, and it's the first thing that you would think of when you write this query.
How do I?
Right.
Yeah.
So it could be something in between that this query might
false positive.
And you're right. This query itself would find, does not take into account and does not look and checks for if you've actually introduced controls to mitigate and define it, right? So that's what I meant when I said, you start with a basic query, find the instances, hopefully not that many, as in this case 1, and then you can look at it, the results and see and triage that manually. If you find a lot of findings, and as you go, you think of all the possible cases and mitigations that you might have in code bases, then you refine the query, rerun it again, refine the query, rerun it again. This one in particular, you're right, it might lead, it definitely lead and will miss mitigations and mitigation controls, and that would potentially prevent zip slip vulnerability.
Yeah, but if you have like multiple products with the same vulnerability, then it makes sense to have one way of fixing this vulnerability for all the products, like a framework, implemented in a framework instead. So to have like one way, one code, so you can adapt your rule to avoid false positive in the future. Okay.
Yeah, absolutely. And then by just writing that query once and just publishing it or including it in your query pack that you run with CodeQL against all or your whole code base, you will find it, or you might find it elsewhere in other projects where you did not get the bug bounty or a pen test finding in. So you're basically using the bug bounty report from one project to find and fix vulnerabilities in other projects. And
Definitely.
yeah. Thank you. Now I'm gonna finish off with not a practical or public one, a public example and vulnerability that we fixed, but more of a hypothetical one. But it's a scenario which I think we can all agree that it's realistic, and either we have seen it or we might see it. It involves secret scanning and secrets in our code base. I don't have slides for this, and I don't probably need slides for this. What I have here is a organization that I've set up, which is called DZ.org. It has a couple of, 3 repos, and what I got as a bug report is that a secret is available or has been exposed in my public repo in my open book that looks, I don't know, like someone, a bug bounty hunter, has found this secret and has submitted it as a report, right? And I've confirmed this is an actual secret, and we've revoked the token, we've revoked the secret, it's now safe. Is that the best we can do? Now, probably not, because we recognize that this is a secret that we usually generate, and it's called, because the organization is DZ, we usually prepend our secrets with the ZSH as a DZ secret, and then I believe this is, what was it, 36 or something, or 40? Never mind, 40 alphanumeric characters. So we got that report, we fixed this. What can we do more? Now, by utilizing and by using secret scanning, we can define that as a secret. How do we do that? So in our organization, and we want to search for it elsewhere in other code bases and repositories that we'll have, right? What we do here is, now we went to the organization settings and we want to enable, secret scanning. Is it enabled? It's enabled. Let's look at the organizations. So this is one, this is another one. Do we have a secret scanning enabled? We actually do, because I did this before. So what I want to do is now search for those secrets in all the other repos, right? Now, what do we do there? And we are back to the organizational, the settings on the organization, and we are in code analysis. And what we want to do is create a pattern, because a new pattern that we will search for in our repos, right? So we know, let's call it the Z. We define a name, the Z secret, and then we know that the format we use is ZSA and Z secret underscore, and then A to Z. I think it's 36. Let me just confirm this. I'll stop sharing my screen for a second.
I'll entertain.
So
while you check, is
36.
These features are, I mean, CodeQL is enabled for all the public reports, right? So if you want to practice and practice with the rules and use it, it's free for your open source projects.
So as I said, the CodeQL is also run on all open source projects. So what is done? The same holds for secret scanning. There is a set of secrets that GitHub continuously scans for all the public repos, right? So this one in particular, because it's custom one, it's like it's for our internal repos. Non-public ones, we define a custom pattern for it, which of course won't be scanned for all the other ones. I mean, all the public ones, but it will be scanned here.
Yeah.
Am I sharing? I'm not
so it's not yet. So it's 40 or 36.
Yeah, it's 36.
All right.
So what I did is basically used Python to print that as 36 characters.
There you go. You're back with your demo.
Yeah. So if we say the case that we had, it's in our open book app. We can dry run that. It does match query. It's an organization. We're going to save it run. We can dry run it and confirm it in our repos. So it's already found. We run it against the open book where the original bug bounty report came in. We confirm that it works. We did some more testing, and we're going to publish it, right? So once we published it, this will be a pattern or secret pattern that will scan for in all the repos, all the repositories in our organization. We have a new project or another project called New Secret Demo, where what I did is just introduced the same secret, and hopefully by now it should have been found by the secret we've defined from, well, the pattern for secrets that we've defined based on the original bug bounty submission that we had. And now we can find vulnerabilities. Well, we can find the secrets in all our repos.
Cool.
And I think that's it. I now say thank you, and hopefully you can either wrap this up. I don't know. I haven't checked the chat if we have any questions.
No questions at the moment. But of course, if we have questions on our Discord channels, I'll forward them to you. I guess you joined the Discord channel already. If you didn't, just do it. And we can take the questions there. Maybe one question about the secret scanning is, because now we define the pattern, we define a regex, I guess.
Yeah.
But what if I don't have a regex? And of course, I have secrets in my code. Will it detect like the most common names of secrets as well? Like, I don't know, I'm thinking AWS keys or API keys, cold authorization. Like, will it work also on variable or custom names?
Yeah, so it
just mentioned
does look for a secret, right? So the secret has to be in a given format. Now, what we have is set of secrets that are predefined, including, I don't know, the ones that you mentioned, right? So like AWS API secrets and Azure and Checkpoint, and, Checkout, sorry, and so on. So if there is a whole list, so it will find those. But what I showed here is a custom one. So for example, I'm AWS. I want to search for all secrets in my code base that I know are in a particular format. So I define a custom pattern for my organization. That being said, you're right. I mean, there is a set of patterns that we look for, that secret scanning looks for, and of course finds those in your database, in your code base, sorry, and Git history.
Perfect. Okay, so I don't think we have more questions. So, well, Stefan, thanks a lot for this cool. Tell me.
Yeah, I don't know. Since you mentioned it, what we also have is what is called. Let me share the screen. It's just easier. If you are AWS, 1 second.
I wish.
If you're AWS and you know that a lot of people, a lot of companies generate secrets, and they might get compromised by them storing them in their code bases, you can get yourself onto the secret scanning partner program, where you would define, like, basically, if the Z organization was big enough, I would join the partner program with the secret scanning partner program, where I would say, hey, this is my pattern, right? Secret scanning can go about and scan everywhere. Once it finds it, it can submit it to me, let me know, so I can either automatically revoke that secret, and if it's an API key, just make it invalid. Therefore, the moment it gets found, the moment we notice that it's compromised, by being into the partner program, we remediate that and make that window shorter. Like, as soon as we find it, we'll revoke that secret and make it invalid. So if you are AWS, you can reach out with your custom pattern, join the program, and then all code bases, and my secret scanning is also scanning all the open source projects as well, will be identified all throughout the code base.
We'll let you know when I become AWS. Okay. No,
looking forward to the day.
Well, we'll call you. Yeah. All right. So, well, thanks a lot. We have a Nicola. Enjoy listening. Yeah, I also enjoyed it a lot. Hopefully, everybody. I mean, the video will be available on the YouTube channel. So, for whom couldn't join today, then can rewatch it. They can rewatch it whenever they want, day and night. So, so for today, that's it. I just want to say that on the 15th, we will have another event scheduled, and it's called Stranger Danger. Your Node.js attack surface just got bigger. So join our meetup group. It's in the chat, and you will get all the updates with the events, location. We will try to do it in person this time. This one was also supposed to be in person, but last minute changes, and we're almost in person. But next one, we will try to do it in Amsterdam. So join us, join me, Liran, that we'll have a cool talk on Node.js. So everybody, thanks a lot. Stefan, thank you very much. And we will meet soon, I guess. And with the rest, we'll see you on the 15th.
Yeah, thanks for inviting me. Hope the talk was useful and interesting for the audience and you. And yeah, let's do the next one in person. I'll definitely be there.
Yeah, I mean, we can always do a workshop of a few hours, building CodeQL queries, right?
We can do that. That'd be fun. Yeah. Pick a vulnerability and code a query and contribute it to the
community.
To the community.
Yeah. All right. Okay. Thank you, everybody.
Thank you.
Bye-bye.